So the first question is, why are there intergenerational transfers in many species? If we imagine a species that doesn't make intergenerational transfers, then we might ask whether at some younger age, a member of that species would, if it could, choose to borrow some resources to invest so it could develop more quickly, grow more quickly, and so on. If the answer to that question is yes, at some interest rate that corresponds to what can be achieved by intergenerational transfers, then there may be the potential for natural selection to lead to transfer of behavior. But I've gotten a little ahead of my story, which is that we conceptualize the life history strategy as being limited by a budget constraint, which says that at any age you acquire a certain amount of energy and then you allocate it among growth, among fertility, and maintenance and survival. So when you're very young, you have a lot of growing to do, you've got to avoid predators and so on and so forth. And it might well be a time in which there'd be a very high return to having incremental resources. And it might be that for an older adult, that incremental fitness return is less. And so it might be fitness improving for this genetic line for the older to make some transfers to the younger. These transfers are not an exchange. They're not repaid. They are something that, well, in a system of transfers, they will be repeated from generation to generation. So generation N makes a transfer to generation N+1, makes a transfer to generation N+2, and so on and so forth. It never comes back to the first generation. These are downward transfers, as Jonathan was just saying. Okay. So I'm going to talk about a couple of modeling efforts. One of these is within the mutation accumulation approach. Another is within the optimal life history approach. And in both of these, the result is that intergenerational transfers, downward intergenerational transfers, co-evolve with longevity. Intergenerational transfers, well, parental care is the simplest form, and of course it's very pervasive. So, let's suppose now that we are looking at a species that does make intergenerational transfers. The question then is, how might this practice, evolved practice of making intergenerational transfers, how might that then shape the evolution of other life history traits, in particular longevity? So Hamilton argued in his classic 1966 article that the force of selection against deleterious mutations that affect mortality at a given age, the force of selection against such a mutation will be proportional to the share of lifetime reproduction that remains after that age, survival weighted, and so on. Well, this share of remaining lifetime reproduction will be at its highest point up until sexual maturity, say for a human, maybe at 15 or something like that. And then as we age beyond that, a diminishing share of lifetime reproduction is in front of us, and the force of natural selection against any mutation that raises mortality at that age will be weaker and weaker until we get to menopause. Remaining fertility is 0, and mortality rises catastrophically, the so-called wall of death idea. Okay, so well, that sort of sets the stage for thinking about the way intergenerational transfers might affect this mutation accumulation story. And the idea is very simple. The article is a mathematical article, but the idea is just that if older people are continuing to contribute to their reproductive fitness by contributing to the success of their children and grandchildren by making transfers to them, then indeed natural selection will still care about them in some sense, and there will be perhaps a diminished but still positive force of selection to remove such mutations from the population, and we would then expect post-reproductive survival instead of mortality that rises catastrophically after menopause. In the theory I developed here, instead of the Hamilton result, there's something sort of symmetric, which is that now the force of selection for mutations affecting mortality after a given age is proportional to the Hamilton type effect, a weighted sum of the Hamilton effect plus a transfer effect. And the transfer effect, just like the remaining fertility effect, is the share of lifetime transfers made to others that remains to be made after a given age. And if we think about that, that share starts at 0 at birth, because the transfers have to balance out over the life history and in the population cross-sectionally. So that share is 0 at birth, and then as we receive more transfers as we age, looking to the future, we're on net going to be making more transfers because they're no longer balanced by those transfers we received earlier in life. So we get a rising share of lifetime transfers remaining. It peaks at the age of economic maturity when we become nutritionally dependent and then begin to make transfers to others. And then as we move through our life making transfers to others, the part that's remaining declines again. So the idea is that the force of selection against a mutation raising mortality should be proportional to that shape of net transfers of the life cycle. And we just saw it on the slide in the previous talk. We saw the current net transfer profile. Okay, so what are these weights? Well, for a species that doesn't make transfers at all, the weight's 0 on the transfer component, and we just have the Hamilton model again. For a species that has evolved an optimal trade-off between quantity and quality of offspring, that is to say, it has chosen investment in transfers to offspring and numbers of offspring such that they've maximized their fitness. For a species like that, a slight variation in fertility, say a slight increase in fertility, is completely offset in its effect on fitness by the reduction in transfers per offspring, just as we find from those experiments on clutch size, on a number of surviving chicks in the next generation and so on. Whereas an increase in resources available for transfer translates into a proportional increase in fitness. So in that case, the transfer function gets a weight of 1, and the Hamilton fertility effect, remaining fertility, gets a weight of 0. And I think in nature, most cases are going to be somewhere in between. So this is a diagram from that 2003 article. The green line is showing, so we have log of mortality on this axis. The green line is the prediction of the Hamilton theory. We have flat, very close to 0, infant and child mortality up until the age of reproductive maturity. This was a sort of anomalous prediction of the theory that made Hamilton uncomfortable, which he was well aware of. And then, as we move through the reproductive years, the share of remaining fertility declines and mortality rises, and that's the prediction. Now, this blue line is the prediction of the transfer theory for the optimally evolved quantity-quality trade-off. So we have the decline following birth as the share of remaining transfers over the life cycle rises, and then once we reach economic maturity and begin to make downward transfers ourselves, then mortality begins to rise, and we have something like that. And I've plotted this against Aceh mortality, this black line, and against Swedish mortality, that red line. And I should say, by the way, this blue line is calculated based on Hilly Kaplan's data on Aceh and a couple of other groups. So there's, to my eye, I'd say this is really quite a striking correspondence. I don't know if fit it would be the right word, but I want to hasten to add that really it doesn't have any business doing that good a job, because the world is much more complex than this, and food calories and caloric transfers, it's a very small part of what parents and other older adults do for the young, and anyway, that's what this looks like. Okay, so then there's a work on optimal life history, in which we start with some constraint about the trade-offs in the budget constraint, the trade-offs between spending energy to reduce mortality or raise fertility or grow more rapidly in relation to how much can be foraged. And I'm not going to go through all that math, but there's a whole series of papers that develops these ideas. And it leads to the conclusion that there will be a U-shaped pattern of mortality over the life history, including post-reproductive survival. This is developed for determinate growth species, and that's specifically incorporated in the setup, but I won't go into that here either. This is sort of in words the result we find for juvenile mortality, that is in determinate growth species. You grow, initially you grow and survive, and then later you survive and you reproduce, but you don't grow and reproduce at the same time. So this is for the juvenile segment of that life history. And again, just as in what I was describing, we get a kind of weighted sum of the Hamilton effect in the numerator and the transfer effect in the numerator. But we have some new stuff here in the denominator that has to do with the fact that if you invest earlier in growth, then you're going to be bigger next year. You'll be able to acquire more energy yourself. You'll be able to grow more. You'll be able to acquire even more energy, and so on. This is the compounded growth effect. And so the earlier you have a growth, the bigger the payoff. If you wait until you're 14, then you'll miss this sort of compounding effect. So you get something that's a product of these, and then eventually on how much body size affects fertility. So this leads to a declining pattern. And generally, I'd have to say, this is, as Ken Wachter said, you can't get any real quantitative predictions out of this. You make a ton of assumptions you hope are realistic, and you try to get some qualitative insight, I would say. And then on the adult mortality side, again, we have a Hamilton effect, and we have a transfer effect, and then we have in the denominator something that looks different under optimization than it does under mutation accumulation. I think I'm going to skip over that. Okay. So that's the work on the evolution of longevity, and it also includes evolution of transfers and evolution of fertility. There are other topics here on which there are papers developed in this same mode of analysis, which I won't spell out. But the most recent one is this evolution of menopause with an adult division of labor and the possibility of upward transfers towards the end of life. And that's done in a two-sex with the invadability of mutation type format. Okay, 3. Now, you solve some problems, you create some greater efficiencies, you raise fitness by introducing intergenerational transfers. But when they're heavy intergenerational transfers, you've also created some problems and some inefficiencies. And the first problem is a parent dies, you may lose several or all of your offspring. So you've linked the survival of your offspring to your own survival, and that could be tremendously inefficient. And there's an enormous incentive, as it were, to raise fitness by finding some sort of life insurance arrangement. And social sharing arrangements in which you're living with other kin, or perhaps you're also living in a larger sharing group with unrelated kin, can help. It's not perfect because the survivors may kill your kids instead of feeding them, but it's an improvement. So that's the first problem that is created by the intergenerational transfers and that social living and sharing arrangements can help to resolve. The second one is that, as we've known since Shayanov's writing in the early 20th century, there's a systematic variation in the dependency burden over the life history, over the history of reproduction of the family in humans. Approximate doubling of the dependency ratio as you, say, move from the start of a mating union through your 25 or so reproductive years. The dependency burden doubles, and then, again, we saw this data on depression of young adults and so on. Well, that's very consistent with this sort of view. So it's because of the need to continue to support these dependent offspring that this dependency burden becomes so crushing for humans. And again, by living in a larger sharing group with perhaps with more kin, but also with non-kin who may pitch in, you can alleviate this problem. Not remove it altogether, but soften it. So now let's suppose we have social living, we have transfers, we have social living. Now we have a new set of problems and distortions and inefficiencies that arise from the fact that we have become social animals sharing food. Once the whole point of being in such an arrangement, in part, is that parental survival is going to matter less. So there's less strong selection in favor of parental survival. And possibly we are less long-lived than we would otherwise be. That's the first point. The second point, once you have food sharing, then other people are helping to raise your kids. And so the cost of fertility, the energetic cost to you of fertility is reduced. And you may have more kids, you may evolve to have higher fertility than you otherwise would. And this may be inefficient because it's brought about by a kind of free riding. It's not that individuals are deciding to take advantage of the situation, it's that evolution is deciding to take advantage of the situation. So that's the second point. A third point is that if you're in a closely related kin group and an infant of yours dies, it's not a great energetic loss. The energetic costs of pregnancy and a few months of lactation are relatively small compared to the enormous costs of feeding and caring for a child for 18 years or whatever it takes in a hunter-gatherer group. So when that child dies, you have recovered that 18 years of costs you had planned for, as it were, and you can use them for other things. First of all, you quickly get pregnant and have another kid, and in the meantime, the siblings can eat this food, the parents can be better fed, and so on and so forth. There's not such strong selection against infant and child mortality, I'm suggesting, in a close kin group, as there is when you're in a larger sharing group, perhaps with non-kin or with more distant kin, because in that setting, when the infant dies, you've not only lost the costs of pregnancy and lactation, you've also lost the 18 years worth of assistance you were going to be getting from the other members of the group. And so it's very costly, and the selection selective force against infant and child mortality in that social setting is going to be higher. Okay, I think that's what I wanted to say about that. Now, to explore some of these issues, Carl Bow and I, and initially Tim Miller, designed a microsimulation program, which I don't have time to explain in detail, but the basic idea is there is a demography that's specified. Individuals are reproducing. At each birth, there are new mutations introduced. The mutations affect survival at older ages, and so on and so forth. Food consumption raises fertility, reduces mortality. Okay, so if you're in a sharing group and there weren't any older individuals, you're going to consume less, you'll have lower fertility, and so on and so forth. So the survival of elderly matters. Now, we run this thing with mutations occurring. We run it for different lengths of time, but here's 75,000 years. That would be typical. And things settle down and they become completely replicable. It'll look like there's a lot of randomness here, but there's not. There's almost none. This is just to show the effect on infant survival of having a mother alive or not. The M stands for matriarchal. These are the smallest sort of sharing groups that are assumed in this model. And if you only have your mother around to provide for you and the mother dies, you have extremely high mortality. You might possibly be saved by a grandmother or something of that sort. And then these are larger sharing groups. This is sharing groups of up to third cousins. This is a sharing group of 8 to 25 people, which seems to be ethnographically realistic. That would include maybe 3 or 4 of this kind of group. And here, kin are sharing their food 50-50 with the group, and 50-50 they're keeping just for themselves. Here we see evolved age patterns of mortality under different assumed social living arrangements. So the matriarchy is this green line. And here we see a bulge in mortality say, the teen years. Those are going to be years partly when you are at higher risk of having your mother die, and partly there's this life cycle squeeze, so you're consuming less well, so we have higher mortality there. But generally, you see that infant and child mortality are higher than in these broader social sharing groups, consistent with what I was saying a moment ago. And here we have, this is the way mortality would evolve under the Hamilton specification. This is assuming that all sharing is at the level of the population, whereas these lines are assuming that sharing is within kin groups, so it actually matters whether you survive or not, because you're the ones who are going to be taking care of your kid. And you see generally there's post-reproductive survival, and then things get complicated out here. And I'm not going to discuss why they get complicated. I'm going to leave it at this, just to say that the social organization affects the life history evolution in interesting and understandable and important ways. The last thing I want to do is put some of these social groups in competition with one another to see which one does best, which one wins the battle for greatest fitness. And the way they compete is that foraging success in these simulations depends on population density. So as the population gets denser, it's harder to get food. In every other respect, in all those respects, these different social arrangements are programmed exactly the same way, except that they have different living arrangements. So we have we'll have 3 different populations that are matriarchal. We'll have 3 that are this up to third cousin arrangement, and 3 with 8 to 25 members, each with a number of these up to third cousin type groups. Here we have the log of population size. Here we have the cycle. So this is going up to 3,000 cycles. That would be 15,000 years. And what we see is that the matriarchal, all 3 matriarchal populations are rapidly going to extinction. And the 3 with most sharing, size 8 to 25 and so on, they are winning out, and you see that the up to third cousin is also going to extinction. So this is showing the efficacy of the broader social sharing, avoiding maternal mortality, avoiding the life cycle squeeze, and so on. However, this outcome results when we turn off an effect in the simulation model. We turn off the effect that childhood consumption raises adult foraging efficiency. If I turn that feature on, which is consistent with the last session we had on the long reach of childhood and these effects persisting over generations, then we get exactly the opposite result. Now the matriarchal social arrangements win out, and the largest group vanishes. How do we understand that? The way I understand it is that when you have this big payoff to having a well-fed kid, and that can be transmitted intergenerationally because the well-fed kid grows up and forages successfully and feeds his kids or her kids well, and so on and so forth, then the variance is good. You may lose a high proportion of the left tail of this distribution, but all you need is a few that work out really well fed, grow up strong, and so on, and they become a sort of long-term, well-fed, highly productive, very effective group. So I'm going to leave it at that. I'd say, yes, we become more and more social. Each step in higher sociality solves problems and creates new ones. I guess that's the bottom line. So the first question is, why are there intergenerational transfers in many species? If we imagine a species that doesn't make intergenerational transfers, then we might ask whether at some younger age, a member of that species would, if it could, choose to borrow some resources to invest so it could develop more quickly, grow more quickly, and so on. If the answer to that question is yes, at some interest rate that corresponds to what can be achieved by intergenerational transfers, then there may be the potential for natural selection to lead to transfer behavior. But I've gotten a little ahead of some transfers to the younger. These transfers are not an exchange. They're not repaid. They are something that, well, in a system of transfers, they will be repeated from generation to generation. So generation N makes a transfer to generation N+1, makes a transfer to generation N+2, and so on and so forth. It never comes back to the first generation. These are downward transfers, as Jonathan was just saying. Okay. So I'm going to talk about a couple of modeling efforts. One of these is within the mutation accumulation approach. Another is within the optimal life history approach. And in both of these, the result is that intergenerational transfers, downward intergenerational transfers, co-evolve with longevity. Intergenerational transfers, well, parental care is the simplest form, and of course it's very pervasive. So, let's suppose now that we are looking at a species that does make intergenerational transfers. The question then is how of my story, which is that we conceptualize the life history strategy as being limited by a budget constraint, which says that at any age you acquire a certain amount of energy and then you allocate it among growth, among fertility, and maintenance and survival. So when you're very young, you have a lot of growing to do, you've got to avoid predators and so on and so forth. And it might well be a time in which there'd be a very high return to having incremental resources, and it might be that for an older adult, that incremental fitness return is less, and so it might be fitness improving for this genetic line for the older to make. Might this practice, evolved practice of making intergenerational transfers, how might that then shape the evolution of other life history traits, in particular longevity? So Hamilton argued in his classic 1966 article that the force of selection against deleterious mutations that affect mortality at a given age, the force of selection against such a mutation will be proportional to the share of lifetime reproduction that remains after that age, survival weighted, and so on. Well, this share of remaining lifetime reproduction will be at its highest point up until